Okay. So we can slowly turn back. And so the next speaker is Rangeet Bhattacharyya from the Department of Physical Science in the Indian Institute for Science and Educational Research, Calcutta. So please.
Thank you, Gonzalo. And I would like to thank the organizers for the invitation. So I'm part of Indian Institute of Science, Education and Research, Kolkata, and I'm in the Physical Science department. And we have a lab, spin lab, so where the work that I'm going to show, it's basically the contribution from the entire lab. So we do experiments and theory both. The experiments are like NMR experiments, spectroscopy. And the theory we do this quantum master equation, and that is largely motivated by what we see experimentally, some of our observations. Now, in NMR, it's a spectroscopy. So we look at quantum systems connected to a thermal environment, a thermal bath. And when we try to look at the quantum dynamics, essentially it is described very well by Markovian quantum master equation. But there are certain observation experiments that this master equation, it fails to account for certain behavior, certain experiment we can design. These experiments cannot be described by the quantum master equation, the rate of change of reduced density matrix given by this Hamiltonian. Typically, if we have the drive or coupling that goes in the first order commutator, and this dissipator contains the contribution from the environment, the system bath coupling. But as it is, it cannot explain certain experiments. For example, one of the recent experiment which are being done, which is spin locking. So in this spin locking experiment, I would like to show you how it works. So if you have in NMR, we have many spin, let's say very simply spin half particle, many of them, and they're Zeeman split, and you have a net magnetization. You flip the magnetization, let's say along x direction, and then you apply a drive along the x direction. And when you do that, if you have a dipolar coupled system, spins have dipolar coupling, and they are not in a liquid, in a solid setting, so that means the dipolar vector is not changing as a function of time. What you see is the locked magnetization decays extremely slowly. They almost seem not to decay. So this is why the term came, the spin locking. But of course, after a very long time, we see that the magnetization vanishes. And in terms of density matrices, when you flip the magnetization, you create a lot of single quantum terms. And while the magnetization is locked, you see many zero quantum terms like sigma plus, sigma minus kind of coherences. And of course, after a very long time, the density matrix is in a diagonal form, mostly. So this is one experiment. It does not have any explanation. Dynamically, if you just put Markovian master equation and try to solve it, you do not get this behavior, not as it is. Then there are other questions. So for example, the drive, in a master equation, the drive goes in the first order. But if the drive, if we control it, like we create an engineered noise, a stochastic term, should it not go to a dissipator in the sense like for the spins, it's not possible to distinguish what comes from the bath and what comes from a stochastic drive. And also there is this problem with rotating wave approximation. So if we apply a drive which has a non-resonant component, it gives a Bloch-Shigert shift, it is none. But typically the way we derive the Bloch-Shigert shift is a second order contribution of the drive. But the perturbation expansion, which leads us to the quantum master equation, that is not applied on the drive. So to get the block triggered shift, we have to do yet another operation and put this term by hand in the master equation. So overall situation is a little uncomfortable. This equation largely works, but there are minor bits and pieces where it does not fit in, and that gives us the motivation to look at the derivation of master equation once again. And we derive it very differently. So again, I mean, our motivation is NMR spectroscopy, where the spins are embedded in molecule. So each spin or system, it is connected to local environment. It gets influenced by local environment, and this collection of all the molecules, like a big water bath, that is the thermal bath. So it's a collection of local environment that constitute a bath. Then each local environment, each molecule can undergo fluctuation. They are undergoing translational, rotational, and vibrational motion. So fluctuations, we try to incorporate the fluctuation in the master equation by adding an explicit Hamiltonian. These fluctuations are acting on the bath, on the local environment. So the way we do it is this chi j, these are bath eigenstates for the bath Hamiltonian. And so we assume a diagonal Hamiltonian. So the individual elements fj, their strengths, these are Gaussian and delta correlated stochastic variables, so they are fluctuating. So visually you have bath levels, and bath levels are undergoing fluctuations. They have one advantage. If you have a bath coherence, such fluctuations, they ensure that the bath coherences die. So that means the bath remains in thermal equilibrium, even if it develops a tiny bit of entanglement with the system, but these fluctuations will ensure that the bath density matrix remains diagonal. So overall, we have a system Hamiltonian, we have the environment, and then any other interaction, drive, or interparticle interaction of the system, we call them H effective, and then we have the fluctuations. So these are the total set of Hamiltonians. And to construct the propagator, next thing we do is we solve Schrodinger equation, u dot is equal to minus IHU. We expand the propagator one time and split the Hamiltonian. We are in the interaction representation, so that means the Zeeman term for the spins, or the main part, the time-independent part of the bath Hamiltonian, those are taken care of. So we only have the H effective, which contains the drive, interaction, and system bath coupling, and the fluctuation. We split them up. And then we club this identity and this HL part, and we make an assumption. I mean, if you look at this propagator, the system Hamiltonian is already in the first order, and we believe, I mean, we make an ansage that all preceding evolution is due to fluctuation. So this U can be replaced by UL. UL is the full Hamiltonian, full propagator due to the fluctuations alone. So when we club them up, the final propagator looks like UL going from T to T1, and then an integral T to T1, H effective T2, and UL T to T1. This propagator, we plug it in the coarse grain derivation. So we take von Neumann-Liouville equation, integrate it from T to T plus delta T, and plug in this propagator. And after that, it is the usual steps, in the sense like we use the cumulant expansion of this combination of UL. That gives us a kernel. This kernel is essentially coming from bath fluctuation, and this kernel regularizes any kind of divergence that may appear here. So essentially, this is our master equation, where we have all Hamiltonian in the first order. Of course, the system bath coupling does not contribute in the first order, that vanishes, but we have the drive and dipole. And here, we not only have the system bath coupling, which gives us the standard dissipator, but we also have something from the drive as well as the dipolar coupling. Or there could be cross terms as well. So this master equation, we have the regular master equation, but adding new terms. So if we use this master equation, try to derive the block equation, we get the usual block equation, like We are taking a two-level system, applying a drive with a offset delta omega. So we have this delta omega offset, and there's say the drive strength omega 1 and the regular relaxation terms. But the additional dissipator that comes from drive, that gives us a couple of decay term and a shift term. See, all of them, they have a Lorentzian spectral density, the dissipator from the drive. So let's look at the shift part first. These are dispersive Lorentzian. And in the limit, when tau c is large, these are the shift terms that we get from Fluctuation. So if we have a linearly polarized drive, the non-resonant part of the drive, that is giving a shift term. That shift term, we get it dynamically here. So it is one perturbation expansion, including the drive and system path coupling. The drive part gives a decay and a shift. That is one big advantage. We do not need any separate RWA for this master equation. And the drive terms can have a second order effect, the dissipate. So after we came up with this block equations, we tried to experimentally validate it. The trouble is, what we say, the one easy way of detecting the drive-induced dissipation would be that you notate the spins. You apply a drive and just create a Rabi oscillation scenario. If the drive is faster, the faster Rabi oscillation, then if drive-induced dissipation is there, it will decay faster. The only trouble is, in the experiment, oftentimes we encounter what you call radio frequency inhomogeneity. The drive does not have same amplitude everywhere. So as a result, you have a first order decay, which is not coming from the dissipator. We refocus that using a rotary echo technique, where we apply a pi and minus pi pulse can be applied, and the magnetization does not have any first order contribution, but it was on the YZ plane doing the notation all the time. And we generalize that sequence by pi, then minus 2 pi, and then pi, and apply it many times to find out how the decay rate depends on the Rabi frequency, and we find quadratic dependence, exactly what we expect. Also, I mean, like in the case where this denominator of the Lorentzian is small, this decay rates, they are also proportional to the fluctuation correlation time. Tau c is the correlation time of the fluctuations. What we find that as we increase the temperature, tau c is going down. So one can estimate like h by tau c should be of the order of kVt. So with increasing temperature, the fluctuation correlation time going down, that kind of intuitively makes sense. So after we verified the master equation, and this is the shift term, by the way. So shift term, experimentally known for a very long time, that the shift should be a dispersive Lorentzian in the inverse of detuning, and our theory exactly predicts that. Now, having verified this master equation and formulated, so we look at the spin locking once more. And the spin locking we try to explain, and before that we look at certain recent experiments where the spin locking was performed. Initially, the locked magnetization oscillates. So initially there would be an oscillation, and then there is a region where the locked magnetization does not seem to change. Here the time axis is in log scale. So it is, you see, it's a couple of orders of magnitude in time when the magnetization remains locked, and after a while it goes down. So this decay is mostly due to system path coupling. So all the dynamics that is taking place here, including a dissipation, that takes place much before the system path coupling starts acting on it. So that means you can assume that during this period, the system behaves like a closed system. The bath, it did not start affecting it yet. So which means that this part can be thought of a pre-thermal phase, a pre-thermal plateau. And so this was actually the experiment motivation, was to recreate the pre-thermalization in a closed system. The natural explanation comes from Fluctuation. So you have a dipolar network. and you apply periodic kicking and try to use Floquet to show that a many-body system give rise to a p-thermal plateau. We are trying to look at it from a different point of view. But before that, this experiment actually originally was done by Redfield. So the same Redfield who gave the master equation. Redfield's master equation paper came out in 1957, and he was a very good experimentalist. So he did this experiment in 1955 on a set of solids, and he found that this lifetime of coherence is enhanced the much longer quasi-steady state as a spin-locked state. So after Redfield, this was studied by NMR people, Leavitt, Suter, and Ernst. They realized that the quasi-equilibrium state must be a linear combination of couple of constants of motion. So before the bath started acting on it, if you look at the overall Hamiltonian, you have dipolar interaction, you have drive. So if you look at the constants of motion, then a density matrix must be a linear combination of those. So that part was studied, but it was still a dynamical picture was missing. So we try to look at this problem this way, that we take a dipolar system, just to spin, and add the dipolar interaction, Ising and exchange term. These are secular terms, they commute with the Zeeman part. And we also have the non-secular part, fast part. We have the drive, and this is in the acting on both the spins, they're identical, and then we have a system-Bath coupling. So using our master equation, now we have a couple of Lindbladian form, secular part of the drive, secular part of the dipolar interaction, and then from non-secular part we have another dissipator, and from system-Bath coupling we have yet another dissipator, so many of them. And of course, to analyze it, first, we take only the slow part, and we realize that the final density matrix must be a linear combination of the eigenvector of the Liouvillean with zero eigenvalue. So these are the eigenvalues of the Liouvillean, so all are nicely negative, except the zero eigenvalue has degeneracy. So there are multiple constants of motion, dipolar order, pre-thermal order. They have zero eigenvalue for this Liouvillean. And these are the dynamical set of equations which describes what happens to the system. Of course, we could have written it in terms of the density matrix itself, but this is a much closer to the NMR language where I try to write everything in terms of expectation values. So using this, we get the same behavior that initially there would be oscillation and there would be a plateau kind of behavior. Of course, the plateau does not last long. The moment you add the dissipator from the other part, the non-secular part of the dipolar interaction, that gives you a dissipator, and this dissipator lifts the degeneracy. And net result is, after a very long time, you see the plateau slowly decays. So that completely captures the experimental behavior. But the big quantity that plays important role here is the second order dipolar coupling that normally quantum master equation cannot capture. Then we have a cross term between drive and dipole. And we also have a dissipator from the drive itself. So these three terms, they appear in all equations. These are crucial in making the initial decay. The initial magnetization decays to the plateau value, and then of course it stays. So that comes from this new dissipator which we did not have previously. So this is our explanation. Then spin locking can have multiple plateau. Experimentally, it has been shown one plateau, but it is possible if you start with a different initial state, you can have multiple plateau. That is possible. So after having explained the spin locking part, we look at what happens when you apply a strong drive to a system. Now, this FRQME, fluctuation-regularized quantum master equation, it can handle strong drive as long as the drive amplitude squared times the tau c environmental correlation time. That product is much smaller than the drive amplitude, so that the convergence happens. If you apply that, I mean, then essentially, if you have a simple two-level system or simple quantum system, you have the drive in the first order, you have a dissipator, and you have the dissipator from system environment coupling. We are not assuming the spins to be coupled here. We are talking about isolated systems. So if we have a strong drive, the dissipator from the drive would be much stronger than the dissipator from the system environment coupling. And then we expect the first two terms will give us a quasi-steady state. The initial, wherever we start with, initially there would be a dynamics, but this dissipator will take the system to a quasi-steady state, and the system environment coupling will start acting on it much later. So this phase that we have seen during the spin locking, but there the dipolar part also played a role here. This part is only coming from the drive. So this would be the generic behavior. And what we see is this kind of help explain, help create a dynamical model for measurement. Measurement in the sense like we know the simple Born rule. You start with initial state, and if you are measuring an observable, then after the measurement, post-measurement state can be described by a mixed density matrix. Mixed density matrix with the system is in one of the eigenstates of the observable with probability, which is the projection of initial state onto that eigenstate. So is there, I mean, what we are trying to do here is basically this process trying to find a set of equations which gives us the initial state to the final mixed density matrix using our master equation. But before that, a bit of history. I mean, like initially, this pre-measurement that if you have a system and couple it to apparatus, it is possible to have a system apparatus Hamiltonian, which will give you a set of entangled states where you will have unique apparatus state for every observable eigenstate of the system. But then collapse part, of course, von Neumann did not discuss. I mean, and then Everett later showed that although it is possible that you can do that, but it is not guaranteed that there would be a unique choice of apparatus basis. And much later, Zurek gave this, he asked this question into what mixture does the wave function collapse, and gave the clue that measurement kind of might be kicked by the environment. Environment might be playing some role here. So we are trying that the local environment with fluctuations, they might be playing some role. And we are using this quantum master equation straight. So what we do is, this is our equation, the rate of change of density matrix. We have the drive here, this is the drive dependent dissipator. There is this system environment coupling, but we are only trying to describe what happens in region 1 and 2. So we are, for simplicity, we are keeping it out. It is a small term. And the drive is basically the observable that I would like to measure. And this omega is a strength of the drive. So if we take this master equation and then very simply try to calculate how each element of density matrix evolves under this, then it is straightforward that all off diagonal terms, I mean, we are in the basis where the drive is diagonal. This is in the basis of the drive. So in that basis, density matrix may have off diagonal terms, and it is clear that this equation will give you final steady state where the density matrix, only that part of the density matrix will survive which commutes with the drive. Everything else will vanish. But then the part that commutes with the drive, that gives you exactly the Born rule part. So it is fairly straightforward that if you plug in any kind of generic drive, take any density matrix, and the act of measurement would be applying a drive sufficiently strong, and then after sufficient time, the density matrix of diagonal elements will go, and you retrieve the simple the mixed density matrix given by the Born rule. This is the pictorial depiction, the same thing that I mentioned, that density matrix has diagonal term, which are the Born rule terms, and the of diagonal part, the density, the drive is essentially diagonal, but it has a dissipator. This dissipator will ensure that this the cross of diagonal terms all vanish. So this is the Born rule density matrix, and then we explicitly calculated that on a state of a two-level system which is on the Bloch sphere at a generic point, and try to show that when you try to measure sigma y, the diagonal terms are as predicted by the Born rule, and the off-diagonal term, because of this decay term, gets smaller and smaller, and eventually you have in the asymptotic limit the same density matrix, which only contains a statistical mixture of this phi1 and phi2 two eigenstates of sigma y. So this is yet another application of FAQME. Finally, I would like to talk about one more application of FRQE. There are many. I mean, we are also working on cavity QED and others, but here I will only focus on quantum control part. So one experiment that happens in NMR or optical spectroscopy, a pretty common experiment, is you have a two-level system. It has a resonance frequency, and you apply a chart pulse. So it's basically a frequency sweep. You start the sweep much away from the resonance frequency and slowly cross the resonance frequency and go to the other side. The easy way of understanding this is you write down the Hamiltonian. This is the offset. This offset is a function of time. So this is a linear function of time. So it's a linear sweep. And this is the drive amplitude. Then the adiabats, by diagonalizing this Hamiltonian, these are the adiabats. The adiabats connect the ground state to excited state in the traditional sense, or excited state to ground state. So if your system is in, let's say, originally ground state, and if you sweep it slowly, it will stay on the adiabat. So you completely move the system from ground state to excited state. It's a very standard method. And this leakage rate, that was calculated by Landau and later by Clarence-Zener. So Landau-Zener transition is from one adiabat to another adiabat, and it is given by exponential minus pi omega square by twice r. So omega 1 is the amplitude of the sweep, and r is the sweep rate. It's a linear sweep. So this Landau-Zener transition, I mean, it is clear that if we want a clean transition, ground state to excited state, and no leakage, a perfect transfer, then for any given rate, omega 1 should be sufficiently high. We have to apply a drive which has a very large amplitude, and that will ensure that the leakage is small, and this is the probability to follow the adiabats 1 minus p, and that gives us the perfect transfer. We are looking at this problem from the point of view of a quantum master equation. What we are trying to do is we simulate it, and this is the unitary behavior. So this is excited state population. Initially, there was no population in the excited state, and then as you sweep, this gray line that shows you the particles going to the final state. And then if you have drive-induced dissipation, then the behavior is drastically different, and not too surprising, because if you have the drive, the dissipator from the drive, it tries to saturate the two levels. So of course, I mean, you will not ever have a full transfer. The fidelity of the operation will always be less. Okay, you cannot transfer it perfectly. So on Bloch sphere, it looks like the gray lines, they take your. So gray lines basically shows a spiral-like behavior. So what happens is this Hamiltonian, its effective notation axis, initially it is along minus z, and then slowly the axis goes to from minus z to it goes up plus z, and the magnetization as expected, it is just following the density matrix, following the Hamiltonian and going from the minus z to plus z. But if you have a dissipator, then of course the it is not on the Bloch sphere, it is inside the Bloch sphere because of the dissipation. It still goes up, but the net magnetization is much, much less. And then we were looking at, I mean, it is of course clear that when you are sweeping, if you stop the sweep, if you do not let the drive-induced dissipation act for long, then you get better transfer than in the long term. And that is very different from what you get from the unitary picture. In the unitary picture, once the particle is in the excited state, it doesn't matter whether your drive is on or off, it will continue to stay there. But with the DID, the efficiency is lower. So we stop when we have at the maximum point. And there, for each rate, we can see if we vary omega-1, the drive amplitude, for each rate, there is an optimal value of the drive amplitude which gives you the maximum fidelity, the maximum transfer. So this is a bit surprising in the sense like, I mean, earlier we knew that we just have to apply drive beyond certain value, but now we see that too hard a drive, too strong a drive will not be very effective. So this is yet another our recent result, and so this is theoretical. I mean, we have not done the experiments yet. So these are essentially what we were trying to do. And finally, I mean, these are the two examples on quantum control and the spin locking part. This is what I wanted to show you, and I would like to summarize. So essentially, this fluctuation-regulated quantum master equation, it explains temporal evolution of spin locking that we could not explain previously. And this emergence of prethermal plateau, it is due to the secular Hamiltonian. And this decay of the prethermal plateau is due to non-secular Hamiltonian of the dipole and also from system-Both coupling. And this omega naught tau c, this factor, the Larmor frequency and the tau c, their product, it plays a key role that I have not shown, but I'll tell you. If the tau c is too small, if the product is much less than 1, then you do not get any prethermal plateau. It just decays as a simple exponential. But if the value is large, then you have a long prethermal plateau. So that kind of explains the spin locking, why we see it in the solids, but not in the liquid, even if we use a liquid crystal. And then it can help us with a dynamical model of measurement. And for chart pulse, the population transfer, that gives us a realistic value that why the high pulse in chart does not work. It reduces something we knew experimentally. And we have other explanations and other works going on that I cannot show you, but we are working on Stern-Gerlach on quantum peaks, sensing, storage, entanglement, inertia, etc. And these are our group. And most of the works done by Saptarshi, he is in TU Berlin now, and Nilanjana, she is in Trinity College, Dublin. So that and either Kolkata. Thank you very much.
So we have time for questions. There should be some microphone there.
Oh, very nice talk, Rangeet. You talked about measurements and you try to apply these master equations there. Did you also look into other things like Zeno effect, quantum Zeno effect?
Any specific example?
Yeah, you try to apply, you try to get mixed state from pure state using master equation, right? From measurements.
We see, I mean, like the theory that we try to do, it's fairly generic. So, I mean, like we did not apply it on any particular state that way or particular gate that way. It's a generic measurement.
So, do you think you can also extend further and study quantum Zeno effect?
Possibly, yes. But I would like to tell you about another result which I did not show. It is like, it has something to do with the quantum operation, not measurement. So you have a quantum system and you apply drive. And this purpose of the drive is to move the system from in the Hilbert space from one point to another. Okay, so I mean, like basically what we are trying to do is initially you are here and you apply a drive to move it to some other point. But if you have a drive-induced dissipation, that means the final result will be a mixed state. So you do get this one, but you also have, this is an unwanted path, okay? Because of this dissipator, you end up at different places also. But that is clear that it will reduce your fidelity. So this is another work where we found that, like for CNOT gate or any other gate, if you try to do a quantum operation, if you try to do it very fast to satisfy the DiVincenzo criteria that operation must be done in a much shorter time than the environment starts influencing it, then you have to have a very large Rabi oscillation, large drive, so that you can do it quickly. But that gives you a lot of dissipation. So that dissipation actually, that means you can say that too strong a drive is bad, but if your drive is too weak, then the system path coupling, it takes too long time, system path coupling will kick in. So net result would be for a quantum operation, you have an optimal speed. So that we did work. So, I mean, I don't know whether that answers your question.
Yeah, we can discuss.
Quantum operation.
But, I have another question.
Yes.
So I think in most of the simulations, you have assumed one spin half particle, but how easy or challenging it is to extend to multi-qubit system with different relaxation parameters?
Beyond a couple of spins, 5 or 6, if you try to do full Liouville space, then it is computationally very tough. You need a big computer to
You think you
simulate
can go up to 5 qubits?
Yeah. So, but we do simulate up to 5 or 6 spin, including everything, meaning coupling between all spins and drive and etc. So it is possible, but beyond that, we need special simulation technique. I mean that it will not.
Are there other questions?
I have just a quick question about this extending to multi-qubit case. So there, when you are modeling the local environment, you are taking the fluctuations to be delta correlated in time. And that is needed for Markov unity. But in the case of many qubits, it could be the local fluctuations of the local paths could be correlated spatially with each another, right?
Possible. So in such cases, I mean, like this is a standard result in known that if you have a two quantum system connected to a common path, you get a persistent entanglement. This is the old result. I mean, like, so if you have taken such a system where you take a multi-qubit gate and they are connected to a common environment, then of course you will get persistent entanglements. But usually what happens, I mean, at least the CSA part in NMR term, the one of the relaxation Hamiltonian, that is local. So as a result, you do not have persistent entanglement. Your local environment approximation works very well, even if all the spins are part of same molecule.
We can have time for a last question. Now let's thank the speaker again.